Welcome to lecture 37. This lecture we're going to be talking about air standard analysis. This is an introduction lecture for the remaining lectures in the course. So today we'll give this air standard analysis introduction. It's just a way that we analyze the upcoming cycles in the next few lectures. And then in the next lecture we'll talk about the Otto and diesel and dual cycles. These are typically used for internal combustion engines, like in your car, for example, or in trucks and such. Then after that, we'll talk about the Brayton cycle and Brayton cycle improvements. The Brayton cycle is used in jet engines, which is another type of internal combustion engine. It's just not a reciprocating engine like you might find in a car. So the air standard analysis is used in all of those different cycles. So once we get through the Otto, diesel, and dual cycles, and then the Brayton cycle and Brayton cycle improvements, then we're done with the course. So the end is in sight. We're getting pretty close to the end of the semester. So to get started here, as I mentioned before, the air standard analysis is just a technique that we use to investigate internal combustion engine cycles. So the picture I have on the screen here is of a typical internal combustion engine you might find in your car. You can see a piston inside a cylinder here attached to a crankshaft down here. You can see a valve open right there. We're going to take a closer look at this later in the lecture. I highly encourage you to take a look at these YouTube videos that I've put here on the screen. The first one is an old video. This is more of a 1950s, 1960s style old educational video, but it does a pretty good job of describing the basic technology. Now, it'll focus on older style car engines, things that have a carburetor and such, which we don't really have nowadays. But it's a good video, and I highly recommend you take a look at it. I can't remember how long it is, but it may be on the order of 10 minutes long. The second video is a newer video showing newer technology in engine design. It's from Toyota, so you'll see that name mentioned a few times in there. It has some pretty good animations. So it shows, again, some of the basics of engine design and then some of the newer improvements to help with efficiency of the engine. And then the last one is quite a different video. This one's longer. I think it's about a half an hour long. It's very much a hands-on video. So it's a guy who goes through and shows real engines and all the various parts and talks about them. That one's a really good one for seeing actual parts and hearing someone who works on engines just talk about those parts. So after you've gone through the first two, definitely take a half an hour and watch this third one so you can see how these various engine components look in real life. All right, well, let's get started with the material. So in the next lecture, we're going to be talking about reciprocating internal combustion engines. So these are the kinds of engines in your car, very common. You have spark ignition engines. These are common in most passenger vehicles that we have in this country. And then we have compression ignition engines. So these are more like, so the spark ignition engine, we'll talk in the next lecture. Those follow what's known as an Otto cycle, O-T-T-O. You can jot that down here, O-T-T-O cycle. And then the compression ignition engine, those follow what's known as a diesel cycle. So the compression ignition engine, those are typically found in bigger trucks. They're more common in Europe in passenger vehicles, not so much in the US. The difference in these is just how the fuel-air mixture gets ignited. So in a spark ignition engine, like in the picture I have down here, what happens is the fuel-air mixture gets ignited with the use of a spark plug like you see here. In a compression ignition engine, what happens is the piston compresses the air to a very high pressure, high temperature, and then a fuel injector injects the fuel into that high temperature air, and it ignites just because it's at a high temperature. So it's using the compression process to actually do the ignition. You don't have to make a spark to start the ignition process. So in a diesel engine, it's the high compression that causes the fuel-air mixture to combust. So that's the difference between these. And then you'll see in the next lecture more thermodynamically why those cycles look a little different. So the components in an internal combustion engine are shown here. You'll have multiple of these in a typical vehicle. So this is just one cylinder with one piston. So the cylinder, of course, is the outer part. Here you have your piston. The piston is connected to the crankshaft down here. Up here, this shows two valves. In modern engines, they may have 4 valves, 2 inlets and 2 outlets. So one of these, like this one, might be the inlet valve where the air comes into the cylinder In an older engine, it might be air and fuel coming in. And then you have an outlet valve where the combustion products leave from the piston. So after they're ignited, and then the piston comes back up and pushes the combustion products out, they would go out through the outlet valve. And the piston will go up and down. The distance that it travels is known as the stroke. So it goes from the bottom, we call this the bottom dead center. That's the very bottom that the piston goes to. And then it goes through the stroke all the way to the very highest point, and that's called the top dead center. So these are typically abbreviated TDC for top dead center and BDC for bottom dead center. There's a little bit of volume up here when this is at top dead center. You know, the top dead center might be to this point right here. That would be the piston face. This little bit of volume right up here at the top is called the clearance volume. The entire volume from the top dead center to the bottom dead center is known as the displacement volume. So let me just write that down. Displacement volume is going to be the volume at the bottom dead center minus the volume at the top dead center. So that's the displacement of the piston cylinder system here. So the total displacement, when you hear like a vehicle has a certain liter volume, so like an engine has a, I don't know, 2.6 liter volume, that total volume is the sum of all of the displacement volumes of all the different piston cylinder arrangements in the vehicle. If it's a 4-cylinder engine, it would be 4 times the displacement volume, and that gives you the total displacement volume for the engine. Obviously, the way this is set up, the piston goes up and down. There's a reciprocating motion because it's going around the crankshaft. The crankshaft is ultimately connected through the transmission to the wheels of the vehicle. The work done on the piston face because of the combusting gases ultimately gets converted into shaft work through the crankshaft. All right, so just a few bits of terminology here. The ones that are kind of important are top dead center, bottom dead center, stroke, and displacement volume. We'll refer to those frequently. We're going to focus on what's known as a 4-stroke cycle engine. It's very, very common. It's the most common type of engine design. There are some other ones. That third video, if you go up to this third video here, he briefly talks about some other kinds of engine designs. For example, like a Mazda has a rotary style engine. But we're going to focus on the most common, the 4-stroke cycle engine, and I'm going to talk about all the various processes involved in this 4-stroke cycle. The first part of it is an intake stroke. So here what happens is you have an intake valve, that's this valve right here, that opens up, and the fuel-air mixture comes in. During that part of the intake process, the piston is moving downward. You can see that it's moving down here. So the piston is moving down and it pulls in the fuel-air mixture, right? So this is going down, this valve's open, fuel-air mixture comes in. Then we move on to the compression portion of the cycle. In this, what ends up happening is the piston starts moving upward and it's compressing that fuel-air mixture. The valves are closed and the fuel-air mixture gets highly compressed. Then we have the power cycle. This is the portion that we generate power in. Now that we've compressed the gases to a high degree, the spark plug ignites the fuel-air mixture. And when that ignites, it causes the gases to expand. It goes up to a very high temperature and pressure here. And that high pressure pushes the piston down. So you can see the piston is now moving downward. So that pushes that piston downward, and that's where you generate the power from to turn your crankshaft. Once that goes all the way down, it'll come back up into the exhaust portion of the cycle. So you can see the piston has been pushed down, and then it'll come back up. And now it's coming back up. What happens there is the exhaust valve opens. You can see it open here. And then these combustion products, the fuel-air mixture that has now been combusted, it's getting pushed out by the upward movement of the piston, so it goes out. So those are the 4 different strokes in this 4-stroke cycle. The crankshaft actually revolves around twice during these 4 strokes. You can sort of see it illustrated graphically in these images, and I'll refer to it again in the next plot. Well, I'll refer to the 2 revolutions in just a moment. But before we do that, we're going to talk about what's known as an air standard analysis of this process. Okay, so the real-life process here is highly complex. You're dealing with real materials. There's a mixture of fuel and air with different properties. Perhaps the fuel is atomized, so it's maybe in liquid droplets and some vapor. You've got frictional effects. These are metal walls, so there's some heat conduction that can occur through the walls. You've got material coming into this piston, material going out through the exhaust valves. It's quite complicated. The combustion process is also very complex thermodynamically. It's very complex. Okay, so in ME200, we're not going to learn enough to be able to analyze a real engine and predict numbers accurately. It's just too complex. You have to study engine design both experimentally and computationally. It's just, you can't do it all by hand. However, we can develop a highly simplified analysis of this kind of four-stroke process that we can analyze by hand. It's called an air standard analysis, and it's just highly simplified. So in this, what we call air standard analysis, it'll be a highly simplified analysis, and it'll just provide qualitative understanding. It'll give us trends. The quantitative values you get out of this for pressure and temperature are not going to be accurate, but it will give you qualitative trends. For example, if I change the displacement volume, what effect does that have? If I put in more heat during the combustion process, what impact would that have? So that's what I mean by qualitative understanding. So it's highly simplified to provide qualitative understanding, not quantitative understanding. The simplifications that we'll make will include having a fixed mass of air. So we're not going to model air coming in and air going out during the intake and exhaust processes. Instead, what we'll do is we'll close these valves. They'll be completely closed, and it'll always be the same quantity of air in the cylinder. So it's a system analysis, not a control volume analysis. It's always the same mass of air. In addition, we're not going to model a fuel-air mixture. It'll just be air. Right, so we're not going to worry about any of the chemistry involved in that process, and we'll model the air as an ideal gas. Right, so it's a fixed mass of air modeled as an ideal gas. Again, we're just making a simplified analysis, something we can do by hand. The combustion process, of course, that's very complex, a lot of chemistry involved there. We're not going to model that. Instead, we'll treat it as a heat addition process. When we're in this part of the cycle where combustion occurs, what we're going to do is just instead model it as some heat coming into our air. Okay, so that's how we're going to treat that. Again, just simplified. I already mentioned there's no intake or exhaust processes because we're dealing with a fixed mass of air. The exhaust portion of the model is going to be modeled as a constant volume heat removal process. Once we have the combustion, the heat coming in the real engine, what happens is that hot combusted product air-fuel mixture gets exhausted, right? It gets pushed out of the cylinder by the piston through the valve there. So that's what happens in real life, but in our model, this valve is closed, and instead we're going to get rid of the heat through heat transfer out of the cylinder. Okay, so we're not going to get rid of the air-fuel mixture, we're just getting rid of the heat. So that's that bullet point. And then the very last one is we're going to model all of the processes as being internally reversible. Again, very highly idealized. In real life, that's not the case. There's a lot of irreversibility occurring because of frictional effects, viscous effects in the fluid, the mixing involved, combustion chemistry. Those all involve irreversible processes, but we're going to ignore those and treat it as all being internally reversible. It's kind of like the frictionless spherical cow approach to the analysis. So that's called an air standard analysis, and we're going to do that for our Otto, diesel, dual cycle, and Brayton cycle engine analyses. Okay. Now we can go one step further and do what's called a cold air standard analysis. And the cold air standard analysis, it's still an air standard analysis, except when we model the air as an ideal gas, we'll go one step further and treat the gas as having constant specific heats, which really just means that we're modeling, instead of an ideal gas, we're modeling a perfect gas. It just simplifies the analysis even further so that we don't have to use the ideal gas tables. Remember that for an ideal gas, the way we find properties is through the ideal gas tables. If it's a perfect gas, then there are some closed form formulas that we can use instead. We don't have to go back to the tables. All right, let me show what a typical PV diagram looks like for this four-stroke cycle. So the various parts on that cycle, we have the pictures over here on the right-hand side corresponding to the parts. The bottom is the volume, and you'll see that it goes from bottom dead center to top dead center. Remember, the bottom dead center, that volume is going to be larger than the volume at the top dead center. Right? So when we go from bottom dead center to top dead center, the piston is moving upward. Right? We'll start here at the intake portion. So we're going to start right here for intake. So intake, what happens is we move from top dead center. The piston's originally up at the top here. And then the piston moves downward. The piston is moving down. You can see that here. All the way to the bottom dead center. So the intake valve is open here. Then the intake valve closes here. So we've gone down. Then we have the compression portion of the cycle where the piston moves upwards. So now we're going from bottom dead center back up to top. So we go all the way back up, and pretty close to the top dead center is when combustion initiates. That either occurs because of the spark plug, which is shown here. The spark plug ignites the fuel-air mixture, or if we're dealing with a compression ignition type of engine, like a diesel engine, what happens is the fuel gets injected at this point, and then the high temperature of the gas, when it's been compressed, automatically ignites the fuel-air mixture. So you'll notice that what we did is we went from top dead center to bottom dead center, and now we're back at the top dead center. So the crankshaft has moved around one whole cycle here. So that's one whole rotation of the crankshaft to go from intake to the compression process. Now that we've ignited the fuel-air mixture, we get the power cycle. So the pressure goes up, and we push down on the piston face. So we're over here. We're pushing down on the piston face, so the volume gets larger because we're pushing the piston down. So we're headed from left to right in the plot, so the volume's getting bigger. And then we get close to the end of that power cycle, and what happens is the exhaust valve opens right over here. Okay, so now we're at the bottom dead center where piston's all the way at the bottom, and then it'll come back up toward the top to push out the exhaust. So this is the exhaust cycle, so that's our exhaust stroke, so that's this one right here. So we're pushing the gases out. So this going from here over to here and then back again is another rotation of the crankshaft, right? Because we're going from top dead center to bottom dead center, piston's all the way at the bottom, and then we come back to the top dead center, so it's gone around one revolution. So in this 4-stroke cycle, the crankshaft is rotated around twice. So you can kind of see that here. Now, when you look at this PV plot, this is a typical PV plot that you might get from a real experiment. You can sort of see the complex behavior of that. We'll talk a little bit more about this kind of plot in the next lecture, but what we'll end up doing in our air standard analysis is we're going to ignore the PV behavior in this exhaust and intake portion, and we're just going to idealize this path, the cycle, in our auto and diesel cycle analyses. So we'll come back to it again in the next lecture, but just imagine this path. If you were trying to idealize it, what kind of path might you follow during compression? What kind of path might you follow during power cycle? How about the path during combustion? That looks almost vertical. Since it looks almost vertical, maybe that's a constant volume process. Same sort of thing down here. When you do the exhaust portion, ignore this, just treat this as being vertical. Right? So I'm getting a little ahead of myself here, but the idea is let's just kind of imagine idealizing what that cycle looks like. And that's what we're going to do in the next lecture. There are a couple of parameters that we sometimes use to describe the behavior of these cycles. One is known as the mean effective pressure, or MEP. This is defined as being the net work out of the cycle, so the net power that we get out of it, or the net work that we get out of it, divided by the displacement volume. So this is the displacement volume, just the bottom dead center minus the top dead center. If you look at that, it's like work over volume, right? Do you remember for PDV work? So PDV work was like pressure integrated over the volume. It looks like pressure times a volume. So that's why this is called a mean effective pressure. This is a type of the units of pressure. It's like the units of work over the units of volume. So it's kind of like PDV here. It's called the mean effective pressure. It's just a comparative measure. If you have two engines with the same displacement volume, the one with the higher mean effective pressure will give you a higher amount of energy or work out of it. So if it's the same displacement volume, a higher mean effective pressure means you get more work out of it. If you report the mean effective pressure for a certain displacement volume engine, it's just a comparative measure. I know this mean effective pressure is higher than that mean effective pressure, so I know which one's going to give me more work. The other quantity that we're going to refer to in the next lecture is known as the compression ratio. This is just the volume at the bottom dead center divided by the volume at the top dead center. So it just gives you a ratio of the volumes, just how much we're compressing the air inside the cylinder. And this, you'll see in the next lecture, can be related back to the thermal efficiency of the cycle. And we can either do this in terms of the actual volumes or specific volumes. Since the mass of air remains constant through this whole cycle, we could do this in terms of specific volume rather than actual volume. And as you might imagine, the compression ratio is always going to be greater than 1 because the volume at bottom dead center is bigger than the volume at the top dead center. The last thing that I'll talk about is just what we're going to do in the next lecture. So we're going to consider what I call 2.5 cycles. We're going to talk about the Otto cycle. So that's your spark ignition engine, typical passenger vehicle engine. The diesel cycle, this is the compression ignition type of engine. This would be more for like big trucks and such. And then a dual cycle, which it has elements of both. That's why I call this one's like the half. So 1, 2, and a half. Because the dual cycle is a combination of both of these. So we're going to analyze those in the next lecture. And what we're going to do then is we're going to talk about the paths in that cycle. So the 4 strokes will idealize in different ways for the Otto and diesel cycle. So we'll talk about what those paths look like. We'll draw those on PV and TS plots. Then we'll apply the first law to each of those paths so that we can determine ultimately the net work out of the whole cycle, right? And that net work is going to be found from our PDV kind of work, right? So we'll calculate that throughout the cycle. We'll also calculate the heat transfer in and the heat transfer out during the combustion and exhaust portions of the cycle. Once we have that information, we can calculate a thermal efficiency for our internal combustion engines. And then along the way, we'll make use of this definition of the compression ratio and the mean effective pressure because these are common terms, especially the compression ratio. It's used frequently in discussion of internal combustion engines. So we'll put our analysis here like the thermal efficiency in terms of the compression ratio. And then we'll ultimately observe some trends. If we increase the compression ratio, what happens to the thermal efficiency, for example? That's what we're going to do in the next lecture. And then the very last thing is just something for your convenience. What I did is I took a picture of table 9.1 out of your textbook and just duplicated it here because since we're going to be dealing with an ideal gas and a perfect gas, it's just nice to have one place where all of the aspects of the ideal gas model and the perfect gas model are listed. So you can see here the ideal gas law, how we find internal energy and specific enthalpy for an ideal gas. These are all for ideal gases. Constant specific heats, this is our perfect gas. They don't call it a perfect gas here, but that's what I call it. What happens if you assume that you're dealing with a perfect gas, and how you calculate changes in specific entropy for constant specific heats or variable specific heats. By the way, just for the variable specific heat, so this is the ideal gas, the difference in specific entropies is not S0 minus S0, right? This S0 value, this is not specific entropy. What I'm highlighting here, that is not the difference in specific entropy. The difference in specific entropy is this one right here. Okay, S0 is a convenient quantity that we tabulate in the ideal gas tables. It might be less confusing if we used a different symbol than S0. If I just put an alpha there, like alpha at T2 minus alpha at T1, that you'd probably get less confused by that. So if you want to calculate the change in specific entropy for an ideal gas, this is how you calculate it. There's a temperature component and a pressure component. And then, since we're going to be assuming for some of the processes adiabatic and internally reversible, those will be isentropic. And so here are some expressions relating properties if you're dealing with a perfect gas undergoing an isentropic process. And then here are the expressions if you're dealing with an ideal gas undergoing an isentropic process. This is where these relative pressures and relative volumes show up. So this is from table 9.1 of your textbook. All right, with that, I think we're at the end of this lecture. In the next lecture, we'll get to the auto, diesel, and dual cycles.